You ever stop to think how your phone just knows when to flip its screen? Or how some cars can park themselves, sensing an obstacle you can't even see? Well, it's not magic. It is an entire invisible world of technology, powered by these tiny little devices that give our machines senses. Today, we're going to pull back the curtain and explore the fundamental physics behind these digital sensors. We're talking about sensors.
You know, it's funny, this quote from Lewis Carroll really kind of nails it. The absolute best technology, it just blends into our lives until it feels twice as natural, right? Almost like it was always there. And sensors are the perfect example of this. They're these invisible little building blocks that teach our machines how to see, hear, and feel the world, extending our own senses in ways that really are as large as life.
So let's get down to it. What is a sensor, really? Well, the official definition is super broad. A device that receives and responds to a signal or stimulus. And, as our source material points out, that could describe pretty much anything, from a human eye to the trigger on a pistol. But for what we're talking about today, we need to be a little more specific. We're focused on the technological devices that translate a physical property, like heat, motion, or light, into an electrical signal that we can actually measure and use.
Okay, so here's our game plan. We're going to start with the absolute fundamentals. Then we'll look at how sensors fit into bigger systems. After that, we're going to spotlight 3 really cool types: magnetic, ultrasonic, and light, before we wrap it all up at the end. Right, let's start with those fundamentals. Before we can get to all the cool applications, we've got to speak the language of sensors. We need to get a handle on the core ideas that make everything else possible.
So take a look at this really simple system. You've got a person watching the liquid level, and they turn a valve. Now, your first thought might be, okay, the person's eye is the sensor. Makes sense, right? But in engineering, that's not quite how we see it. A sensor isn't just something that perceives. It's a device that's been specifically built to convert a physical property into a precise, measurable, usually electrical signal. The eye is part of the system, sure, but it's not the engineered sensor.
And that brings us to a really important distinction you'll hear all the time: sensor versus transducer. They're not exactly the same thing. A sensor's main job, its whole purpose, is to detect a change in temperature, a change in pressure. A transducer's main job is to convert one type of energy into another, like a loudspeaker, turning electrical energy into sound energy. Now here's the trick. A lot of sensors are also transducers because they convert something like heat energy into an electrical signal. But their primary function, the reason we use them, is for detection.
Okay, so a sensor is rarely the whole story. It's almost always just one small part of a much larger system. A system designed to grab data from the world and then do something with it. So let's zoom out a bit and see that bigger picture, how all these different pieces actually fit together.
Now, I know this diagram looks a little complicated, but trust me, the loop itself is really simple. Let's just follow the signal. It all starts on the left with an object. A sensor detects something about that object. That raw signal, though, it's often a little messy, so an interface cleans it up, conditions it. Then an AD converter does maybe the most important job. It translates that real-world analog signal into digital ones and zeros that a computer can actually understand. The computer thinks about it, makes a decision, and then tells an actuator to do something. And that actuator acts back on the original object. See? It's a complete loop. Sense, process, and act.
So, just to lock that in, let's recap those 5 key players. You've got the sensor, which gathers the data, the interface, which modifies that signal, the AD converter, which translates it into digital, the computer, which processes it, and finally, the actuator, which goes out and takes action in the real world. Every single step is critical to making that loop work. Now, here's a really fundamental way to classify sensors. Are they active or passive? Passive sensors are just incredible. Think about this for a second. They generate their own electricity right from the thing they're measuring. A thermocouple, for example, creates a voltage just from a temperature difference. No batteries needed. It's amazing. Active sensors, on the other hand, they need an external power source to work. They send out their own little signal and then measure how that signal gets changed by the environment.
So what kind of stuff can we measure with these things? Well, as this table shows, pretty much anything you can imagine. We can build sensors to detect sound waves or mechanical forces like pressure, or even the strength of invisible magnetic fields. Each one of these categories is a whole universe of engineering and possibility. This is just a little glimpse into how thoroughly we can give technology the ability to sense the world around it.
Okay, enough theory. Let's make this concrete with our first spotlight: magnetic sensors. We're going to look at one of the most common and useful types in the entire world, the Hall effect sensor. It is a tiny little chip that you will find in absolutely everything,
from the compass in your phone to the anti-lock brakes in your car.
This slide just perfectly illustrates the two main flavors of Hall sensors. The graph on the left, that's a linear sensor. Its output voltage is directly proportional to the magnetic field. Stronger field, higher voltage. Think of it like a dimmer switch. This is great when you need a precise measurement. Now the graph on the right, that's a digital sensor. It doesn't measure, it just decides. It's a simple on-off switch. Once the field hits a certain strength, it snaps on. When it weakens, it snaps off. Perfect for simple yes or no questions.
So why is a simple on and off switch so useful? Well, this interrupter mode is a perfect example. In that first image, the magnet's field is hitting the sensor, so it's on. But in the second image, a little metal vein slides in between and blocks the field. The sensor immediately turns off. What you've just created is a contactless switch, and because nothing ever physically touches, it never wears out. That's why it's perfect for things that happen over and over and over again, like detecting the position of a spinning gear thousands of times a minute. All right, from invisible magnetic fields, let's switch gears to inaudible sound. Our next spotlight is on ultrasonic sensors. These things use high-frequency sound waves, way beyond what a human can hear, to map out the world. You see them in cars for parking assistance, but as we're about to see, they can also be used for something incredibly clever, measuring how fast a liquid is flowing.
The principle here is basically a tiny ultra-precise race. You have two transducers, A and B, on opposite sides of a pipe. First, A sends a little pulse of sound to B. Then B immediately sends one back to A. Now think about it like you're a swimmer in a river. The sound pulse traveling with the current gets a little boost, so it arrives a little faster. The one traveling against the current gets slowed down, so it arrives a bit later. And by measuring that incredibly tiny difference in their arrival times, we can calculate the exact speed of the river itself.
And the physics behind that little race is all wrapped up in this one formula. Now, don't worry about all the letters just yet, just focus on the core idea. The travel time, t, is just distance divided by speed. Simple enough. But the speed part is where the clever trick is. The speed is the speed of sound, c, plus the speed of the fluid if you're going with the flow, or minus the speed of the fluid if you're going against it. That little plus or minus symbol right there, that's the whole secret sauce. That's the mathematical reason this whole idea works.
So this table just breaks down all the variables in that formula. Most of them are things we already know or can easily measure, right? We know the pipe diameter d, we know the angle of the transducer's theta, and we know the speed of sound in the fluid c. The only two variables we're dealing with are the travel time t, which our sensor just measured for us, and the flow velocity vc, which is the one thing we're actually trying to find. So we plug in everything we know, and we can solve for the one thing we don't. It's like a little physics puzzle.
For our final spotlight, let's turn to light. Optical sensors are some of the most versatile and precise tools we have in our entire toolkit, all because they harness the fundamental and sometimes frankly weird properties of photons.
And it all starts with this core equation from quantum mechanics, E equals h nu. All this really means is that a photon's energy is tied directly to its frequency, or you can just think of it as its color. Higher frequency light, like blue or ultraviolet, has more energy packed into each little photon, which is why it can give you a sunburn. Lower frequency light, like red or infrared, has less energy, which is why it just feels warm. At the end of the day, every optical sensor is fundamentally designed to detect these little packets of energy.
Okay, another key property of light is its polarization. Light is a wave, and polarization is simply the direction that wave is wiggling. Is it oscillating up and down or side to side? Imagine shaking a long rope. That's basically it. Now, sunlight is unpolarized. It's wiggling in all directions at once. But when it reflects off a surface, like a lake, it becomes polarized. And by using special filters that can see that change in polarization, which is exactly how polarized sunglasses work, we can learn a lot about the surface that light just bounced off of.
Now this is a brilliant example of putting physics to work. It's a liquid-level sensor that uses a cool effect called total internal reflection. So look at that first diagram. When the tip of the prism is dry, the light from the LED hits the inner surface and perfectly reflects, bouncing right back to the detector. So the detector sees a bright light. But now, look at the second diagram. The very moment that liquid touches the tip, it changes the physics right at that boundary. The light suddenly escapes into the liquid instead of reflecting, and the detector goes from seeing a bright light to seeing nothing at all. It is a completely foolproof switch with absolutely no moving parts to ever break or wear out.
So whether we're talking about harnessing magnetism, timing the echoes of sound, or manipulating the reflection of light, the story is always the same. We are using our fundamental understanding of physics to build technological senses,
senses that are often way more precise and powerful than our own.
So, what's the big takeaway here? Sensors aren't just components. There are proxies in the physical world. They are our translators, converting the universe's fundamental forces into the language of data. They give our technology superhuman senses. And that really leaves us with one fascinating question. Now that we know how to listen to the physics of the world, what else should we be asking it?